Right, so my name is Zach Shmurek-Conti, and I'm a research associate at the Turing Institute here in London. And I would also like to introduce my co-host and co-organizer of the seminar series, David Massagur, who is a PhD enrichment student here at the Turing. So for those of you who are not familiar with the Turing Institute, this is UK's National Institute for Data Science and AI. Also, for the benefit of those joining us for the very first time, I will briefly introduce the topic of the seminar series, that is physics-enhanced machine learning for engineering applications. And physics-enhanced machine learning, as most of you probably know, is an upcoming subfield in machine learning and deep learning that aims to integrate physical understanding of observed phenomenon in the machine learning framework. On a side note, if any of you are interested to share work in any of our upcoming seminars, really encourage you to get in touch with us, as we really have a nice growing community and should hopefully turn into a platform at some point. As for the format of the seminar, our speaker will speak for around 45 minutes, followed by a Q&A, which you may do so either by asking through the chat or by unmuting yourself and asking in person. All right, so without further ado, I'll ask my colleague David to introduce today's speaker, and with that, I thank you all.
Yeah, hello everyone. I'm delighted to introduce here Dr. Wang. Who's going to talk today, obviously. He's an assistant professor of aerospace and mechanical engineering at the University of Notre Dame. He received a PhD in aerospace engineering from Virginia Tech in 2017 and was a postdoctoral scholar at UC Berkeley before joining Notre Dame in 2018. He is now a recipient of the 2021 NSF Career Award, and his research focuses on scientific machine learning that enabled computational modeling, Bayesian data simulation, and uncertainty quantification. So let's hand over to you, and we look forward to what you have to show us today. Thank you very much for offering your talk.
Okay, thank you, David. Thanks for inviting me here. I would like to talk about scientific machine learning in general for computational mechanics, but I will focus on a physics-informed structure-preserved learning for the problem with complex geometries. So I'm not sure I'm showing the correct slides, right? Okay, so just want to make sure. Okay, so before I get started, I would like to acknowledge one of my PhD students and give them the credits for the works I'm going to present today. So a little bit of background. So we know that computational modeling and simulation capability play an essential role in understanding, predicting, and controlling various physical processes like turbulent flows, flow structure interactions, heat flow coupling. So all of this shows complex spatial temporal dynamics. Well, traditional computer models are based on a numerical method like finite difference, finite volume, finite element. And they have achieved significant success in past decades. However, in many practical scenarios, traditional models face significant challenges. First, for many complex systems, the underlying physics might not be fully understood, and our knowledge about the physics is not complete. So it's very hard to directly build a reliable, purely physics-based model. And on the other hand, we know the traditional numerical simulation are often computationally expensive. For example, if we want to simulate this flow structure interaction, it could take weeks or even months just for one model query. So think about it, it's infeasible for the application that requires many model queries, such as uncertain quantification, optimization design, and solving inverse problems. The ever increased data availability combined with recent advances in AI and GPU parallel computing open up new avenues for developing like data-enabled physics-informed simulation techniques for the computational physics, which personally I believe is going to be the next generation computational modeling paradigm. Data-enabled computational modeling is kind of like hot in the recent years, but to formulate a data-driven model, the first thing we need to discuss and think about is the different scenarios of the data availability. If we have a sufficient data, we can go for deep learning, just like those big tech company and use tons of data collected from customers using data mining. However, basically the off-the-shelf purely data-driven deep learning techniques might not be suitable over the entire spectrum of the data availability. For example, if we're talking about the other end of the spectrum, meaning there's no data at all, in this case, what we can do, we probably could only rely on our physics knowledge and build a purely physics-based model. Well, in most of the cases, we're kind of sitting in between. For example, if we only have a very limited data, then we should probably still mainly rely on the physics-based model, but assimilate the limited data into the model to fix unknown or reduce uncertainty, such as to calibrate the models or fuse the data with the model output to achieve the higher predictive accuracy. This is known as the data assimilation. Okay, if we move a little bit further to the left, meaning we have more data, so probably we can leverage deep learning techniques. However, since the amount of data haven't actually reached to the level of big data, we may still need some help to compensate for the data insufficiency. Luckily, as I mentioned, the goal here is to model the physics. So we always have a lot of prior knowledge about the physics to be modeled. So to bake this no physics into the deep learning model seems to be a promising way to go. So here we call this direction as a physics-informed deep learning. It's still a very general concept, but what really do I mean by the physics-informed deep learning and how? So here I would like to introduce some directions that we have explored to showcase how do we actually build this physics-induced bias into the scientific machine learning or deep learning models. So first, we can use the physics to inform the learning architecture design, such as how we encode the physical law or constraints into the neural network by construction without the need of learning them. And how should we build the network architecture to preserve some mathematical structures of the governing equations? So I call this direction as the structure-preserved deep learning. And second, we can use the physics to help the machine learning model training and optimization. So instead of directly learning from the data, we can use the physical law or constraint to inform or constrain or even drive the neural network training. So we don't have to rely on a big amount of labeled training data. For example, if you're familiar with PIN, the physics-informed neural network, the PIN, is kind of in this direction. And moreover, we can further interpret the learned black box model and try to extract the useful information to advance that knowledge of the missing physics. We can couple the PIN with the library-based sparse regression to discover explicit equation for the analytical expressions to directly interpret, for example, the dissuasion-based neural network to discover the PDs. For example, the PD nets is in this direction. So today's talk, I probably only have time to focus on the first two directions. The first part, I would like to talk about how do we actually leverage physics to inform the learning architecture design. And I will introduce our very recent development of the PD structure preserved neural network for predicting the parametric spatial temporal physics. And the second part, I'm going to talk about how do we use the physics to constrain the model training and optimization. It's kind of the PIN, but I'm going to focus on how to handle the geometry complexity. So like I mentioned, traditional computer models face many challenges, particularly for the predicting the complex, the spatial temporal dynamics. In the past few years, many data-driven deep learning models have been proposed and show a great promise. For example, the Smash GraphNet is one of the state-of-the-art deep learning models developed by DeepMind last year, and this model is a purely data-driven neural simulator and based on deep graph neural network to simulate the spatial temporal physics. As you can see, the model has been demonstrated very capable in actually predicting the spatial temporal dynamics for many different physical systems, such as the solid mechanics, fluid structure interactions, aerodynamics flows, or more general computational fluid dynamics problems. And the results are very impressive. Actually, this work has been selected as the outstanding paper in ICLAIR 2021. And our group have also recently developed a novel neural graph operator to learn the spatial temporal dynamics in the mass-reduced space, where the temporal attention is used to enable the long-term model rollout. So with this transformer structures, the long-term predictions is much better than Mesh GraphNet. So this work has been accepted by the ICLAIR 2022. So basically, after training, the model only need an initial condition and some physical parameters like Reynolds numbers or the geometry of some object, and we can make predictions just like the numerical solvers, but in a very fast inference speed. As you can see, the model can deal with unstructured meshes, moving meshes, or even like varying size meshes. And recently, we also demonstrated on the weekly turbulent flows, which I agree with the reference very well. Well, so in general, all of this model are formulated as a very simple structure, as its autoregressive next step predicting structure, meaning the neural network is built to learn the transition from previous dynamics to and then predict the next step. So the backbone network structure of the modern next step models is the residual connections, which is the essential component of the ResNet. So in a ResNet, we know there's a lot of there will be a lot of like blocks of such residual connections. As you can see, in a single residual connection component, the network will output the change from the input layers instead of the value of it. So, but the network structure could be generic. It could be MLP, CN, or graph neural network, or their combination. So here I'm just showing the generic structure here. So as you know, a no issue of this next step model is error accumulation. Since the prediction is based on the model rollout, so the prediction error will be accumulated, making the prediction in the long term unphysical. For example, I'm going to show this animation again. As you can see, the SODA next step models here, like the Mesh GraphNet, they can capture the dynamics at the beginning for this really complex flow, but it becomes noisy and eventually it dominated by the accumulated error compared to the ground truth. And moreover, since it's a data-driven model, so the generalizability could be a big issue in the out-of-sample regimes. The model could have better performance for the unseen initial conditions, boundary conditions, or parameters that are not seen in the training set. And basically, to mitigate the error accumulation, the transition dynamics has to be learned in a very high accuracy. And that means we need a lot of training data. And the training cost would be huge. For example, the Mesh GraphNet requires a very long time to be sufficient to train on high-end GPUs. All right, so to address those issues, like I mentioned, one promising way is to leverage our prior knowledge about the system to be modeled. For example, we may know the physical laws, constraints, or even governing equations of the system. And all this physics might not be like complete or accurate, but we still can use them as some physics-induced bias and introduce them into the deep learning model. So one popular way to do so is to penalize to penalize the violation of the physical law by imposing the residual of the governing equation in the loss function, which will penalize the neural network training. And this is general idea of physics for neural network or PIN. So a lot of work has been done in this direction. However, here I would like to introduce a completely different way of using the physics primers, not the PIN. So instead of regularizing the neural network training in a soft manner by using those physics constraints, so here we're trying to use the governing physics to inform the neural network learning architecture design. So our goal is to design a deep learning architecture that preserves the PD structures of the governing equation by network constructions. So this is motivated by the relationship between the neural network architectures and the differential equations, which has been reviewed by recent studies in the machine learning community. So I'm going to use this simple like residual ResNet component as an example. Let's revisit this residual connections. So in the high level, a residual connection can be shown in this generic form. So where the information from the current layer will go through a black box neural function and output the difference between the current and next layer predictions. So mathematically, this is nothing but can be written as a simple equations. And where T is layer numbers. So what is this? This should look very familiar to everybody, right? If you learn the basic numeric analysis. So this is the Euler discretization of OD. So namely, the residual connection can be interpreted as the explicit Euler discretization of certain ODE. That means, on the other hand, the ODE can be used to formulate the continuous residual connection with infinite depths or infinite number of neural network layers. So this idea is known as a neural ODE, which has been proposed like several years ago, kind of bridge the residual connection with ODEs. And then what about the PDs? We can use a method of lines to convert the PD into a system of ODEs, right? So we need to handle the spatial derivatives, for which we can use the numerical differentiation, such as finite difference, finite volume, or finite element. So the numerical spatial differentiation can be interpreted as convolution operations or graph message passing. So for example, for this spatial derivatives, we can build discrete spatial differential operators based on finite difference, and by applying this 3-point stencil to the spatial solution field. So this can be seen as a convolution operation on this field. So namely, the convolution operations could be interpreted as discretized spatial differential operators. Well, now we bridge the convolution residual network with the PDs in a discrete form. So very recently in the machine learning community, the relationship between the neural network structure and differential equation has motivated new neural network architecture design, where people kind of leverage some features of certain PDs to design desired the neural network with some desired properties. For example, recent NeurIPS paper, NeurIPS paper, they used convection dominant PD to develop a new graph neural network architecture to mitigate the over smoothing issues, which is a well-known issue in the deep graph neural networks. So here, our hypothesis is that we can leverage the governing PDs behind the spatial temporal dynamics to be modeled and to design a novel convolutional residual net for the next step predictions, and which could significantly improve the learning and predictive performance compared to purely black box convolutional next step model. So therefore, we propose to a multi-resolution PD structure preserved neural network for this spatial temporal dynamics predictions. We call it a PBN. So spatially, it's an autoregressive neural solver based on the convolutional network, where the residual connections are constructed by preserving the PD structure of the governing physics and discretized on a low resolution trace. While the encoding and decoding convolution operations with trainable filters enable the high resolution state predictions. Moreover, the network is conditioned on the physical parameters like Reynolds number, geometries. So it can be generalized over a high dimensional parameter space. So compared to the black box next step model, the proposed BBN is expected to be much better in terms of the both training efficiency and out of generalizability for on-C boundary conditions, initial conditions, parameters, and also can extrapolate in time more robustly. So let's see how it works. First, we test it on a 2D unsteady Berger's equation, and the neural model is trained to be generalized over different initial condition and viscosities. That means with the trained model, we only need to provide the initial condition, and given viscosity, the model can rapidly predict the corresponding predicting the dynamics accordingly based on the model rollout. So here I'm showing you two cases where the both the viscosity and initial condition are just generated. The initial condition is randomly generated, and the viscosity on C. So the first column is a ground truth obtained by the high fidelity Mark solver, and the middle is our PBN predictions. While the last column is the state of art black box baseline, which is the same version of the match graph net actually. So as you can see, the black box baseline can only capture dynamics in a very short period, and then the prediction become unphysical. While our PBN agree with the ground truth very well for both the testing case. Now I'm showing more because the initial condition is random field, so we can just randomly generate more testing initial condition and on-C viscosities. Here are another 4 randomly generated initial conditions. It's just like random field in a very high dimensional space. And you can see the soda black box baseline, the last row for these 2 blocks. They deviate from the reference probably at 0.6 t. The capital T is actually training range. But our model agrees with the reference very well, showing great robustness. Please note that here the input dimension is very high. It's more than 6,000 dimensions. So in this problem, we know like the surrogate modeling for UQ in the 6,000 dimensions is notoriously challenging. Let's see how the error propagates in time. So here I'm showing you the model raw errors at each time step, average over 100 randomly generated initial condition viscosity. And so here, this figure, the A is from the training parameter set, and will B is from the testing parameter set. So both, for both, the model are only trained for first like the 100 steps, and it clear that the error for the black box baseline grow rapidly once it step into this extrapolation range, and accumulate the error accumulation effect of the black box baseline become more obvious for the testing parameters, as you can see. In contrast, the error of the PBN predictions remains surprisingly low, even in the extrapolation range for both training and the testing parameters, both the training and testing regimes. There is nearly no error accumulation at all. In addition, the error scattering notably shrink compared to that of the black box baseline, indicating significantly better accuracy, generalizability, and robustness. So we can move to a more challenging fluid dynamics problems. So here we consider this flow with a jet at the inlet. So the angle and the position of the jet can change over time. So the model will be trained to learn the dynamics by changing the jet positions and Reynolds numbers. So here I'm showing you two testing samples where the jet positions and the Reynolds number are different, which are not seen in the training, of course. The left is a little bit like lower Reynolds number of 3,000, and right one is a slightly higher Reynolds number of about 10,000. Again, as you can see the soda black box baseline, they can accurately predict the dynamics at the beginning, but it becomes pretty noisy and non-physical. Clear is showing the error accumulation. And this is more serious for this high Reynolds number, as you can see here. However, our PBN, on the contrary, they are almost identical to the ground truth, even after a long-term model rollout. So from the error propagation figures, this is also very clear. Like no matter in the training and testing regimes, the black box baseline prediction will be dominated by the error after like extrapolation, and while the PBN has almost no error accumulation at all. And moreover, as you can see, the black box baseline has a large uncertainty, while our model is pretty robust. The error scattering remains very low. And please note here, I'm showing you a relative error in a percentage. So the error of the black box baseline is almost like 150% at the very last prediction step. That's why you see the contour, it becomes very unphysical. So in the previous case, the governing PDs are fully no, but you may wonder what if the governing physics is only partially known. For example, we studied the fluid dynamics within a magnetic field, where the physics about the magnetic field is unknown. But since we know this is a fluid dynamics, so we only preserve the null portion. We know it has the convection, diffusion, and the pressure gradient. So how about we just preserve those null portion, but we kind of assume that the magnetic field is not known. So again, you can see the PBN significantly outperforms the black box baseline, which completely diverge after a while the PBN still agree with the ground truth very well. Even the preserved physics is incomplete or kind of inaccurate. So from the error accumulation figures, we again can see here is nearly no error accumulation in our models. It's a slightly higher uncertainty though. So now I would like to discuss the proposed model from the perspective of the differentiable programming. So we know that differentiable programming is a generalization of the deep neural networks, which extend the neural network to more general computer programs that are differentiable and can be trained by backpropagation, just like the classic neural networks. So for example, there are many excellent developments in these directions. From this perspective, particularly from the differentiable numerical solver perspective, our model can be interpreted as a hybrid neural solver, which belongs to differentiable programming. For example, if the governing equation is fully known, the preserved PD portion can be seen as just like one-step prediction of the explicit Euler solver on the coarse mesh. Well, you may consider what if I just use this coarse solver. So here I make the comparison. As you can see, this last row is if we only use the preserved PD part and without any like a trainable neural network component. So it becomes a coarse solver with a very large number of steps. And let's see how it goes. So if we only have the preserved PD portion and formulate it as a coarse solver, even the PD is complete. the predicted physics is far from the reference, as most of vortex are damped out due to the very poor spatial digitalization. Moreover, the large learning step will lead to numerical instability issues. And this becomes worse in the high range numbers scenarios where the course solver just completely blow up in a very short term. So this yellow represents the NAN, it just has no value, blow up. All right, so I think this is the first part of this talk. I just want to give you an idea that how amazing that we can kind of link the neural network structure and with the differential equation and build and preserve some mathematical structures into the neural network and to improve their performance. The second part, I think I still have 20 minutes. Okay, I would like to talk about how to use the physics to constrain the model training. So if you haven't heard about PIN, I will give you a quick introduction. So let's see, we want to build a neural network and to learn some mapping. So traditionally you need a lot of like input-output labels for training. So right, but what if we don't have a sufficient training labels as alternative? And if we know this process should follow certain physical laws or constraints, and we can use this physics to train the neural network by penalizing the violation of those physical laws. So the idea is pretty simple. So a simple way to do so is to modify the loss function by adding the physical constraint in addition to the data loss. So this is the general idea of PIN, very simple, where the different information such as equations, boundaries, and data can be unified in a multi-object loss function. So what would be the issue? So the biggest challenge of PIN is this multi-objective non-convex optimization. For example, here if we use a PIN to solve or to learn the static Navier-Stokes equation solutions. So by simply changing the weighting parameters for the boundary loss, and it can convert to different non-physical solutions. So to improve this, we try to hard encode some constraints such as boundary conditions into the neural network without need of learning it softly. So for example, we developed this boundary encoded PIN for surrogate modeling fluid flows several years ago, where the certain like initial and boundary conditions are encoded in the output layers of the neural network in a hard manner. Namely, the initial and boundary condition will be automatically satisfied by construction. So the training can be constrained by Navier-Stokes equations, which can formulate in a deterministic way, as I mentioned in previous slides. That is to define the loss function to minimize the residual of the Navier-Stokes equation. However, in many cases, we know the data might be noisy and the physical knowledge might not be perfect. You have the model form errors. So in order to consider this uncertainty and make robust predictions, so a Bayesian formulation might be preferred. So here we also constructed a physics-informed likelihood functions, and the posterior of the neural network parameters, and can be learned using the variational inference. So comparing and solving the forward problem, the real power of PIN is to solve the inverse problems. For example, we can use the PIN to infer the near-wall information of the cardiovascular flows, which are very hard to measure from like the 4D flow MRI because the low resolution of the flow imaging techniques. But we can always get some like very sparse measurement. For example, from the PC MRI, we can get some flow information, but just like 2D flow information at sparse cross sections of the human vessels, and we can use that to infer the quantities that cannot be easily measured. So here you can see, for example, like the wall shear stress and near wall velocity, and can be accurately recovered from the velocity data that measured on those very sparse locations using ping. Well, so as you can see, like the ping is formulated to learn the continuous of function or operators in a pointwise manner. So despite the great promise, the continuous formulation for learning the function and operators also face some challenges. First, it requires a massive amount of collocation point in the spatial and temporal domains and a high dimensional parameter space. Therefore, the training cost could be huge. Moreover, it's not easy to impose the boundary condition or other hard constraint exactly, even though I show you there are a way, but if we go to more complex, realistic like scenarios, it's not that straightforward and easy. And more importantly, it's not easy to leverage existing numerical techniques and differentiable programming framework. Therefore, we have explored disparate formulation of ping based on a convolutional neural network and the recurrent formulation to learn the function or operators in a field-to-field, end-to-end manner. So, for example, we can use a convolutional neural network to solve the parametric and Navier-Stokes equations. So the CN is can solve the velocity field and agree with the CFD reference very well. That's great. But the problem is the classic CN had originally been developed for image recognition and processing. So the convolution filters are designed for image on a uniform grade, right? So that's why you can see that most existing works on the PD-informed CN are only able to deal with the problem defined on the rectangular domains with uniform meshes. Otherwise, we have to do the rasterization or voxelizations. So it's very hard go beyond to the regular image-like domains because of the intrinsic limitation of the classic convolution operations. However, in the reality, the geometry is way complex, which needs the non-uniform meshes all the time. So to push forward the discrete ping for complex problems with irregular domains, and we propose two solutions. So the first strategy is to utilize the coordinate transformation technique to map the solution field from the irregular physical domain to the rectangular reference domain. So we have developed this so-called PhyGeoNet, where the key idea is to encode elliptic coordinate transformation into the CN architecture, where the PD is actually imposed on the transformed rectangular reference domain instead of original physical domain, which is irregular. So the elliptic coordinate transformation can be obtained by solving elliptic equations, and which is a deterministic one-to-one mapping, and it can be pre-computed. So there's like no overhead for training the neural network. So now the backbone of the classic CN can be used on the irregular domains. So here is an overview of this PhyGeoNet. It takes the parameters, including like geometries, boundary parameters, and others defined on the physical domains, input channels, and then output the solution on the reference domains. And the boundary conditions, for both directly or Norman boundary conditions, can be strictly imposed by using the constant or finite difference paddings. Okay, and so we don't have any boundary conditions in the loss function. So the loss is only defined by the PD residuals on the reference domain. So now we can learn the solution of parametric PDs without without using any label data. For example, we can use CN to this PhyGeoNet to solve the PD on irregular geometries, like this heat equation on this Batman shape, bat shape, and unsteady Navier-Stokes equation in a patient specific vessels. So the prediction, they all agree with the numerical reference result very well. But here we are talking about neural networks. So the biggest advantage is to learn the parametric solutions in a high-dimensional space, right? We're not trying to use the neural network to replace the numerical solver to directly solve the PDs like in a forward manner. Instead, we want to, for example, build a high-dimensional surrogate, or we solve the inverse problem. So I'm showing you that we use the feature net to learn the solution of the Poisson equations with any like different or random source field. So this source term, the left-hand side, the right-hand side, is a high-dimensional random field. So with a trained model, we can immediately obtain the solution for a large number of randomly sampled source in a second. So here I'm just showing you like a couple of testing samples, which is randomly generated. Okay, so we also compare the proposed discrete pin with continuous pin, demonstrate our proposed is 10 times faster for training and also much more accurate. So the first solution, like I mentioned, is coordinate transformation. It enables the use of classic convolution operations for irregular geometries. But for really complicated geometries, we may need domain decomposition. Otherwise, it's very hard to handle this very complex topology. But as alternative, our second strategy is to directly define the convolution operations on the unstructured data, such as meshes. So we know the mesh can be described as graph, right? We know from the convolution theorem, the graph convolution can be defined on the unstructured data by solving or approximate the eigen decomposition of the graph Laplacian. So we use the graph convolution networks and combine with the Galerkin method to discretize the wig for PD residuals. And here we can build a neural graph or neural Galerkin graph convolution neural network and to solve the forward and inverse PDs just similarly. So let's see. Okay, so I still have some time. So okay, so basically the proposed Galerkin GCN can be used to solve the forward and forward PDs efficiently. For example, such as this linear elastic deformation, or the fluid flows in a stenosis, or this lead-driven cavity flow, which is a benchmark case for many CFD solvers. But I'm not. Nobody is very interested in solving the forward problem because we have a lot of numerical solvers, right? But instead, we are more interested in the inverse problem. For example, if in this 2D structure deformation problem, if the material property is unknown, instead we have very sparse observations from of the deformation. So you can see that using the Galerkin GCN, we not only can reconstruct the entire displacement field, but we can also accurately infer the two material parameters, lambda and mu, after 2000 training iterations. So here, this dashed line is ground truth, true parameter values. So similarly, for this 2D standardized stenotic flows, but we don't know for example, the inlet boundary conditions, the inlet velocity profiles. Instead, we can get some very sparse measurement of the flow rate at those sparse locations. Okay, so we can use the Galerkin GCN to not only reconstruct the flow field from the sparse measurement, but also recover the velocity, the inlet velocity profiles simultaneously, which is parabolic profiles in this case, which is which is unknown in this problem setting. So in general, in this Gherkin GCN framework, we can solve the forward and inverse problem in a unified manner. So for the real world problem, there are still many challenges. So one of my interests is the biometric flows and the cardiovascular flows. So one of them is still like the geometric complexity. So here I will use the last few minutes to talk about it. So for example, for a patient-specific simulation, the parameterization of the 3D patient-specific geometries could be very challenging, right? So this geometry are often reconstructed from the medical images for each patient, and which are very expensive to get the geometric models. Okay, so for the real patient-specific cases, it's very hard to even like parameterize input the geometric space, and it also very challenging to generate sufficient geometric input samples for the downstream like machine learning or uncertainty propagations tasks. So to task this problems, and we want to like discuss how to parameterize the complex geometric space, and how do we generate the sufficient geometric samples. And to tackle this, we develop a statistical shape model. In general, the goal is we build a geometric space spanned by the real patient-specific geometries from the image segmentation, and within the geometric space spanned by the real geometries, and we can generate generate tons of synthetic geometries very efficiently. So this statistical shape modeling includes 3 steps. So first, we build a correspondence among the real geometries, and then we project the register geometry into the latent space, and then we will build a generated model, generate the synthetic geometries by randomly sampling in the latent space spanned by the real geometries. So let me quickly show you like to build the correspondences is actually non-trivial, which is relevant to the mesh morphing. Here we use a large deformation diffeomorphic metric mapping algorithm to achieve that. Here I don't want to go into the details, but the general idea is you build a diffeomorphism by defining the deformation from the one geometries to the other, like the flow, and then the diffeomorphism is obtained by minimizing the difference between the deformed geometry and target geometries. So let me show you. Let me use a pair of the geometry to show you the idea. So here we build the correspondence. This is not my background noise. Okay, so here we want to build the correspondence of the 2 aorta geometries. So we first represent the geometry as a point cloud, and then we use LLDDM to do the morphing, and original geometry will deform to the target and the correspondence is built, and then we can intermediate. Basically the intermediate geometry can be seen as an interpolation of the 2 complex shapes. So imagine that if you have multiple like real geometries, and then we can use this method to span the geometric space. However, we want to deal with this in the low-dimensional latent space. Therefore, we will project the point cloud into the low-dimensional space, such as use the PCA, and each shape will encode as a primary component. Okay, and then we can, within this latent space, we can do the randomly sampling to generate the new synthetic geometries. So I'm going to escape like different sampling algorithm, and in general, basically the range of the sampling space are confined by the real geometries. and you can define it in the primary component space. So I'm going to escape those different sampling methods. And now we kind of parameterize the geometric space spanned by the real geometries, and then we can sample out as many synthetic geometry as we want in a second. So here we have like 8 original geometries from the real image segmentations. And the last 2 rows are some example of the synthetic geometries generated by this algorithm. So with this capability, we can do the downstream machine learning surrogate or uncertain quantification and reductions. For example, here we can build a fast surrogate of the hydrodynamics based on neural network. And so basically give a new geometries and the flow can be obtained immediately. So here I'm showing you like 4 testing samples. The machine learning predicted field agree with the reference very well. Well, the quality of the surrogate, the data-driven surrogate is of course based on the training data. So how to generate the training data also depend on the application scenarios. For example, if we're talking about uncertain quantification, so in the cardiovascular biomechanics, because the geometry is constructed from medical image, which has a large uncertainty because the image has, is sometimes blurred, and the reconstruction can introduce a lot of like uncertainties. So the geometric uncertainty has the biggest impact on the simulated hemodynamics. And however, to like quantify and reduce the geometric uncertainty is very challenging because of like the complexity of the geometric space and how to parameterize. I already talked about that in the previous slides. And also because of high cost of the 3D hemodynamic simulations. For example, we know using MCMC, of course, is always the gold standard approach for the UQ and uncertainty quantification and reduction. However, the MCMC is notoriously expensive as it's sequential in nature and it really requires tons of model queries. For example, in the classic metropolis histine algorithm, we need to like propose usually millions of samples in series, and then their likelihood needs to be computed to determine the acceptance for rejections. So each likelihood evaluation requires the forward model query, make this infeasible for any 3D hemodynamic simulations, right? So to facilitate this process, we can use a machine learning surrogate to pre-filter the rejected samples, while the high fidelity CFD will be only conducted for the accepted samples by the surrogate. And this will significantly reduce the computational cost, as the machine learning inference cost is nearly 0 compared to the CFD. Well, this is known as the delayed acceptance metropolis histine. Of course, the machine learning surrogate can be built offline, but this is not the most efficient way to go, because we always like generate a lot of training samples online in this process. So in this process, we will still use the CFD, do the CFD for the accepted samples. And so those CFD simulation can be recycled and can be used and to build the surrogate online. So we basically developed the active learning based delayed acceptance metropolis histine. Well, the gradual accepted CFD data will be used to train the ML surrogate based on the continuous learning, not the transfer learning. So by doing this, it has several advantages. First, we don't need to generate a lot of offline data, and second, the online collected training data are near the high density region, which is more efficient, which is a more efficient use of the data. And moreover, as we formulate an MCMC on multiple process using the multiple parallel chains, so just one ML surrogate will be shared over the multiple chains. So the online data can be collected from the multiple chain to facilitate the surrogate model refinement and convergence. So here I'm showing you basically the geometry uncertainty reductions. The upper figure shows the orthogonal samples from the prior distribution. As you can see, the velocity are quite different due to the geometric uncertainty. Once the sparse flow rate measurements are simulated in the Bayesian way, the geometric uncertainty can be reduced, and the variation of the velocity patterns is largely like diminished. I think that is all I want to show you, and I would like to acknowledge my sponsors and happy to take any questions. Okay, thank you.
Thank you so much, Jianxun. We have 1 second because I've got some feedback here. Apologies. Right, so I'm aware it's almost 2 o'clock. We might have maybe some questions from the audience. I know there was a hand raised by Peter Yatishin. Okay, there it is. Would you like to ask it?
Hello. Thank you for the talk. It was amazing. I have a question about the first part of the talk, just to make sure I understand correctly. So the convolutions in your neural network that represents the right-hand side of the PDE, they kind of take care of differentiation. So it's a stencil that baked in, right?
Yes.
And then so let's say you are still on a rectangular domain, so something like your burgers example. So then you take a sample of initial conditions, a large sample, and then you solve the PDE genuinely with the solver, and you use that to train your neural network, right?
So in the first part, we use like yes, basically we want to build. So the goal is we want to build a surrogate for the high fidelity simulations, right? So basically we will have some data from the high fidelity simulations, but not a lot. So that is why we want to build the PD structures into the network. So yes, to your question, yes, we will use some data from the high fidelity simulation, but we can also use the data from the for example, the measurement, not necessary to be the high fidelity simulation data. It could be high fidelity measurement data.
The question is, when you're comparing truth with simulation, does it come from the same sample, from the same distribution?
No, not the same sample. No, from testing sample. So the testing are not seen in the training data.
But
so
do they belong to the same distribution though?
So like the training sample will only use the 16. So I don't think the statistics actually matters.
I see. Okay, yeah.
We only use the 16 different samples. So
thank you very much. And the other one, very quickly, the other one is how do you bake in the boundary condition, or you don't, or you learn it?
You can learn it, but you also can bake it. So for example, in the second part of the talk, for the derivative boundary condition, we can basically directly use constant padding to the convolution, right?
Of course.
Or if we're talking about like the Newman boundary condition, you can also use the finite difference padding. So it's also very easy to hard impose the boundary conditions. But for more complicated boundary conditions like a rolling boundary condition, we haven't tried, but I think it is also possible to use like multiple like paddings and to bake it in the networks without need to learn. But you can also learn it from data or put it into loss. So there are so many flexible ways to.
Thank you very much. Thank you for your talk. Thank you.
Thank you for your questions.
Right. Thanks. Thank you so much for the question. Any other questions? Okay. I have one tiny question. I don't know if there's time. Oh, okay. There is another question. Go for it.
No, you can go ahead.
Right.
Go ahead.
Very quickly, with regards to the first part of the talk, I wanted to ask, you are working, of course, in discrete time, right? And the dynamics you recover are, of course, for discrete time. Are you able to generalize towards continuous for a new, let's say, time step? so towards continuous time?
So your question is so your question is can we use that for like for example different time step?
A different time resolution, yeah.
Different time resolution.
Yeah.
Yes, that's a good question. Actually, I have to show you. Yes, the answer is yes. We can do that. But the model I'm showing today in the first part, we just formed it in a one step. Okay. Like next step models, we want to compare with the state of art next step model like mesh graph net. But if we formed this as like a multi-step models and use so if we formulate this more like a solver, it's like multi-step sequence models. We can generate it to like use like different learning step. Like delta t could be different. So we train with delta t and we'll test it on the half delta t is possible. So we actually will recently we'll put a paper on the archive. So there's literally a test case for that. So
That's very cool. I look forward to reading it. Thank you. Okay, so David, go for it, and we'll
Okay. Yeah. Thank you for this talk. It's actually very impressive. I mean, that's the reason why we called you over. I had seen your physics-induced work from one of your students, I believe, and that's why we were kind of very keen, and also to see what was the progress on that. So, and which you have kind of shown. I mean, to be honest, we probably could have invited you for 3 different seminars rather than one, with so many topics you have covered. Well, you're always more than welcome to, for another talk in the future to expand on these exciting topics. I had a couple of questions. One that was not clear from the first part, you mentioned that there was at some point you added some bit that was not fully known, which was regarding the magnetic field or something like that. So in that case, if that, so how does it work? Because effectively, does it mean you don't have the knowledge from the physics? And then, so how were you accounting that part? Was it data-driven then, or how does it work?
So yeah, that's a good question. So basically, to your question, so basically, for some system that we don't know the complete physics, but the physics still like have some, for example, it's like a convection dominant process. So it has the like convection features, right? So if we only know this is like convection dominant phenomena. So the message I want to deliver is if we encode this convection terms into the network architectures, it will help the network learning. So this is different from the solver because we're not only use this term to solve the physics. This is still like data-driven framework. So you have the data to learn the missing physics. For example, in the case I'm showing you, it's still like fluid dynamics, but within the magnetic field. So for the physics about the magnetic field is unknown, but we kind of preserve the convection, diffusion, and pressure gradient. So that will help the learning. So again, it's kind of like the information we know is still kind of useful. If you know if the information you provide is completely like garbage, I think in that case it's not useful. If you are talking about like some very different physics, but you encode a very like wrong equations, that won't help. Sometimes it will like harm the process. That makes sense.
Okay. So sorry, maybe I misunderstood then. So the first part were still data-driven.
Yes, it's data-driven.
Okay. So then moving on to my second question is, you mentioned that those solvers like the physics-induced and the Galerkin one and so on for graph neural networks, they were not interesting for direct for forward simulations. Why is that exactly? Is it because they are computationally, they are not computationally advantageous compared to well-established numerical methods, or what's the reason why you don't see those methods being interesting for forward simulations?
So so for the forward simulation, I'm talking about like the forward deterministic simulation. Just give like one input and you train the neural network and solve it. So in that case, it's not that efficient because to train the neural network, training cost is sometimes is high. And for like if you change different condition, different model input, you have to train it again. So it's not that efficient because we know the neural network is kind of training a neural network is very challenging because you are solving a non-convex optimization compared to the traditional numerical solver. It's more like a convex optimization. So the convergence can be guaranteed that you have like a convergent like order of accuracy. But for the neural network, you don't have that. That is the disadvantage of using the neural network. But if we train the neural network for the parametric solutions, that will be more efficient. So you train the neural network across like a high-dimensional input space, and then after training that, you can use that as a stereo model. The inference speed of neural network is very fast. So I think that is why I see like use a neural network to just to solve a deterministic forward problem might not be that efficient. But for some cases, high-dimensional PDs, you may have the advantage. High-dimensional stochastic PDs may have the advantage. I mean, for the traditional like Navier-Stokes, you just solve it. Sometimes it's hard to beat the conventional numerical solvers.
Yeah. Okay. All right.
All right. Unfortunately, I have to.
I think you mute. You mute yourself.
You're muted.
Sorry. Unfortunately, I have to run off. But if you'd like to continue the conversation, please feel free. I can leave the room open. Before I do so, though, I'd like to say thank you very much, Jianxun. That was really exciting and quite refreshing. And thanks to everyone that's remaining for staying and also for joining us today. Yeah, as I said, if you guys would like to stay on, please feel free to do so. Thanks again.
Yeah. No, thank you very much.
Thank you. Yeah, thank you for inviting me.
Okay, so is there any other question from the audience? I don't think so.